Hi everyone, and welcome to the last lecture of where we talk about matrices. So today we'll be talking about two last stuff that we want to look at while dealing with matrices. One is echelon form, another one is the leading and the free variables in a linear system. So let's talk about echelon forms first. In the method where we use the elementary row operations to find the inverse of a matrix, there are so let's talk about echelon forms. Echelon forms arise when we are dealing with a linear system where the number of equations is not the same as the number of variables, and in those cases we can have these echelon forms, and in fact they are called row echelon forms. And there can be two kind of echelon form. One is just the row echelon form itself, or in short REF, and the other one is reduced row echelon form, that is REF. Let's take an example so that we can see what is an echelon form. Let's say you have a system of 4 variables, but you have 3 equations. So this 4 variable will correspond to 4 columns, and these 3 equations will correspond to 3 rows. So you have a 4x3 system, and the row echelon form of, let's say I want to make a 4x3 system, and let's say our B, that is like Ax equals to B, this B has a form of the following: it has 3 rows and it has 1 column. So our augmented matrix, that is this one, augmented matrix, let's take it to be 1 2 3, and let's denote a dashed line so that we are clear which one is B. So this is B, this will for x1 x2, oh sorry, I'm not putting it here. That pura katna. So let's talk about echelon forms. Echelon forms. We can have 2 kinds of it. One is row echelon, another one is called reduced row echelon. So let's take an example of row echelon form. A thing to note is that this echelon forms helps us where we have let's say I have 4 variables and I have 3 equations. So it is very helpful in finding out which one is a free variable, and we'll talk about it a bit later, but let's try to see what a row echelon form of a matrix looks like. Let's just take the following matrix and I will write it down. Let's call it A, and it has a form of 1 2 3 4 3. Now I want you to notice that I'm putting a dashed line over here because any linear system will have this form, Ax equals to B, and this column will correspond to the B column. and I'm taking some other entries, that is 0 1 1 2, another one is 0 0 0 0 0 over here, another 0 over there. Now notice that this matrix has non-zero rows appear above the 0 rows. What I mean by that is that this is a 0 row, a row consisting only zeros, and these two rows, that is one over here and another one over here, they have non-zero elements. So this is the first property that a row echelon form will have. And in the second property, we can see that in any non-zero row, the first non-zero entry is a 1, that is this one and this one, and these are called leading terms. If you want to think of it as a system of 4 by 3, that is, you have 4 variables and 3 equations. For example, if I had to write down the equation for the first row, this would look like 1.x1 plus 2x2 plus 3x3 plus 4x4 equals to 3, right? This is how it look like, and you would have a similar equation for the second row and the third row. However, this is the reduced form. So as we have started with the reduced form, we cannot actually say anything about the original system, because we have already performed some elementary row operations to come to this point. So as we were saying, that these are called the leading terms. So this is another feature of this row echelon form. And another feature we would like to talk about is the leading one in a non-zero row appears to the left of the leading one in any other row. So what do I mean by that? The thing I mean by that is that, let's say take the second row, and you have a 0 in the first entry but a 1 in the second entry, and the other one that is on the first row happens to be on the left hand side of it. So you can think of it like a stair, like this. It's like a stair. So if you have this structure, then you have a matrix in its row echelon form. And now we would like to talk about reduced row echelon form. That is, we are reducing the row echelon form again. And to make a matrix a reduced row echelon form, that is reduced row echelon form, in short we are calling it RREF, we apply another condition. Let's take it as hash, and this condition is that if a column contains a leading one, if a column contains a leading one, and provided that the conditions or the features we talked about a few seconds earlier, they hold, then all other entries of that column will be 0. Then all other entries of that column is 0. So now we want to separate this board for a second, because at one side we will see a row reduced form, that is RRF, and on the other side we will see an example of reduced row echelon form. So let's take an example. Again, we take the example that we discussed a few seconds earlier. that is the matrix with entries like 1 2 3 4 3 0 1 1 2 0, and the last row is just 0. Here you can see that the features we talked about, taking this matrix as an example, all these are satisfied. But if a column contains a leading one, then all other entries of that column is 0. This is not true here, because this column has a leading one, but all the other entries are not 0, because there is a 0 downstairs but there is no 0 upstairs. So this condition is not fulfilled here, so that's why it's not a reduced row echelon form. But now let's take another example. We want to have let's say 5 cross 3 matrix, and we write the entries as 1 0 3 4 and 5. Let's write 1 0 1 1 2 0, and the third row is simply 0. You can see that this satisfies all the properties that is satisfied by this one, but it has some extra feature. The extra feature is that the leading ones are the only element in their column, that is the only non-zero element in their column. So as you can see, the elements beneath 1 in the first column are 0, and the element in the upstairs and the downstairs both are 0. So this is called a reduced row echelon form. And using this example, that is I'm highlighting with the blue color, we will see that how the idea of free variable arises. So let me just erase this thing up. So now we want to talk about free variables. So let's say we have a system of we have a linear system that consists of 4 variable and 3 equations, that is a 4 cross 3 system, and we perform elementary row operations on it and bring it down to the reduced row echelon form in the following manner. Let's say 1, remember I'm writing the reduced row echelon form over here, so it will be 1 0, let's say 1 1. I'm writing the coefficient matrix first, then 0 1 0 2, and the last row should be 0, right? And you have a 3 over here, 1 over here, 0 over here, and each column will be for one variable. That is, this one was constructed from the coefficients of x1 in all the equations. Similarly, x2, x3 and x4 was constructed, and these are just the coefficient that appeared on the right hand side. B, it also got changed while the row operation was performed. As you can see, we have 2 pivots, this one and this one, but notice that there are no pivots over here. So what that means will be clear in a few seconds. Let's try to write down the equation that this reduced row echelon form gives us. This will be 1 times x1, 0 times x2, 1 times x3, and you have 1 times x4, which is equals to 3. And the second row gives us 0 times x1, 1 times x2, 0 times x3, and 2 times x4, which is equals to 1. And the third is just 0 equals to 0. So simplifying the first equation, we just cancel out this. We have, and the second equation as well. So let's cancel the zeros. We have x1 plus x3 plus x4 equals to 3. And we have x2 plus x4 is equals to, oh sorry, it's there is a 2 over there, yeah, 2 x4 equals to 1, right? So what can we conclude from this? From the second equation, we can see that I can write x2 is equals to minus 2x4 minus 1, right? Oh, sorry, plus 1. And the first equation tells us that x1 plus x3 plus x4 is equals to 3. So from here you can put solve for x4 in terms of x2 and put it over here, but then again you would have x1 and a combination of x1 plus x3, but not x1 and x3 individually. So as you can see, there are 4 variables, but there is ultimately 2 equations. So there is not a unique solution over here. In fact, we have a lot of freedom, and the free variables in this case are x3 and x4. These are our free variables. Why they are called free variables? Because I can write x1 and x2 totally in terms of x3 and x4, just as following. Let's say x1 is equals to 3 minus x3 minus x4, and x2 in terms of x4 as well. So this is how the term called free variable arises, because you have your free variables over here, and for any number, let's say x4 equals to 1 and you can take x3 equals to 0, you can get a set of solution, and if you change their values you get another set of solutions. So if the system is consistent, then for free variables you have infinite amount of solutions. And there is another catch over here, that you can see that this row, after that is the system we took that we haven't mentioned explicitly, after the elementary row operations in the reduced row echelon form, this is a 0 row, right? And here we also have a 0. But instead, sometimes it could happen that instead of a 0 you can have, let's say, 2, and this line will mean that 0 equals to 2. This is not possible, and then you could have inconsistency, that is, the system has no solution at all. Let's say instead of 0 you are having some lambda, and if that lambda was not equals to 0, then the system won't give any solution at all. So if there is no solution at all, there is no relevancy of the free variables or the leading variables, stuff like that. So this is the discussion on the free variables. And finally, the system we are trying to solve is it consisted of 4 variables, right? That is x1, x2, x3 and x4. Let's just see how to write them in the matrix, that is x1, x2, x3 and x4. And remember, we said x3 and x4, these are free variables. So, and we solved that x1 is equals to 3 minus x3 minus x4, and x2 is equals to minus 2x4 plus 1, right? So let's write this down. Now if we write it, this instead of x1 we are writing minus x3 minus x4 plus 3. Instead of x2 we are writing 2x4 plus 1. We leave x3 and x4 as they are, because these are free variables. And what you can do, you can simplify this thing a bit further by using the following decomposition, that is, first write x3, then we are writing minus 1, 0, 1, 0, then plus we are writing x4, and you have minus 1, minus 2, 0 and 1. So this is nothing but just a decomposition. And finally we write the numerical part, that is 3, 1. They are detached, 3, 1, 0, 0. And as you can see, the whole solution is written in terms of x3 and x4. So this is how you can identify the free variables or leading variables in equation where the number of equations is not the same as the number of variables. And with this lecture, I would like to conclude our discussion on matrices and linear systems. Thank you.